Hello, and welcome to episode 21 of CS350 Online. I'm your host, Leslie, and in today's episode, we're going to start a new topic, and that is the topic of file systems, or how we are actually going to store our data on the disk itself. But before we begin, two things. First, an announcement. As some of you may have seen, we have a Piazza post announcing that we are going to have a guest speaker. And that is indeed true. We are going to have a guest speaker. I said I would try to acquire one for this term, and it looks like we have one. And so our guest speaker is going to be Dr. Richard Stallman, who is the head of the GNU project. And I'm sure many of you have heard that name before. And he is going to be talking about why operating systems should be free and all of the software that runs on them should also be free. And of course, if Dr. Stallman wishes to speak of anything else, we are more than happy to hear whatever it is he is interested in telling us. The talk is scheduled to happen not during the episode time, but the plan is to have it this Friday at 3:30 p.m. We're actually going to be doing a test of the tech that we're going to use for the talk this afternoon. To make sure that everything works before we share with you the mechanism by which we are going to be facilitating the talk. But needless to say, it's going to be using all free open source software. So that'll be cool, right? I wish everything was free and open source. The talk is sponsored by the CS Club, which is very generous of them to help pay for the event. And hopefully you will all find it interesting. So once we have done the tech demo this afternoon, I will post all of the instructions for how to participate and to watch the talk. I'll post that all to Piazza later tonight or tomorrow. Now, we're not using Zoom or anything like that, but that doesn't mean that you won't be able to ask Dr. Stallman questions. We are going to be using IRC for questions, and myself and I think one other individual are going to be monitoring IRC for questions and then forwarding them to Dr. Stallman. Now, for those of you who've never heard of IRC or have never used IRC, I will be sure to post some instructions on the channel and the server that we'll be using, and some basic instructions on how to use IRC. It's really, really easy. And if you've ever used Slack before, I want to say Slack is like some pretty paint and additional features sitting on top of IRC. Like, Slack is so like IRC. It's amusing. I personally like IRC. I've been using IRC since 1996. I don't go on very often anymore, but it's a fun thing to do. So all the instructions for that will be coming to you over the next 36 hours to make sure that you are able to watch the talk. And I'm sure it's going to be very lovely. All right, so the next thing is we need to talk about the OS of the day, of course. And we finally reached that point in time where we can actually talk about Microsoft Windows. And by the way, for any of those of you who are watching live, if you notice a problem with my volume, please point it out and I will do my best to adjust it on the fly. It's important to me that the video and audio quality are as best as they can be for you guys. Fun side story. I'm actually going to see if my home network is strong enough to support 4K streaming next term. I mean, if you pay 4K for the course, I should be giving you a 4K video, right? Anyways, Microsoft Windows. So most of you, I'm going to assume all of you, have used Windows at some point in your life. This was released by Microsoft on November 20th, 1985. And Windows 1 is the first one. Yes, there was a Windows 1 and a Windows 2. And these were actually intended to compete with Mac OS. And they were simply extensions of DOS. So when you started your computer, it didn't boot into Windows the way that your computer boots into Windows now. You would boot DOS, and then you would run Windows as like a program. So you'd have to type in the command prompt that you want it to run. And actually, Microsoft Windows actually ran like that for a really long time. I distinctly remember it was around Windows 3.1 a lot of people still had to do that. So I know some computers would boot directly into Windows 3.1, but I want to say that the majority of people, it boot to DOS prompt, and then you had to type like Win31, or I don't even remember because it was like 25 years ago. But you would actually have to manually start the Windows. So these were just extensions to DOS, which means that they had all of the limitations that DOS had. But they've just added a few extra features on top. So you still had a lot of limited multitasking in Windows 1.0. They did have enough multitasking just to support a message loop for the user interface, because you actually want to be able to have a responsive desktop environment. And you're still going to have little to no virtual memory or kernel user program protection. So that doesn't really come in until Windows 2, Windows 3.1. And then we're not going to discuss Windows 2 because it's just, another version of Windows. Windows 1, though, of course, it was a simple desktop UI. And when I mean simple, I mean really simple. So I actually have a photo of it here for you to see, because I thought it'd be fun for you to see. So here's Windows 1. Now, obviously, it's very grainy. And the reason why it's grainy is because this was, I think it was only like 320 by 240 pixels. So you're not looking at like very high resolution graphics. So very, very basic UI, mouse driven. And aside from this welcome screen, windows were not allowed to overlap. So you'll see everything in the background is actually tiled instead of overlapping. So it's kind of fun. This Windows 1.0 wasn't really that popular, but Windows 3.1 was incredibly popular. And this is probably one of my most favorite versions of Windows. It's the last of the 16-bit operating systems. Yes, I said 16-bit. That means that we used 16 bits for virtual addresses and 16 bits for physical addresses. So it's the memory is very limited. Actually, some systems it uses 32-bit physical, but 16-bit virtual addresses. This was very, very popular, and a lot of people used it. It was very easy to use, I found. And it didn't have full preemptive concurrency, but it did do cooperative multitasking. So it could only do a context switch if you yielded voluntarily, so you had to be like a friendly threat, or if you blocked, or if you exited. So there wasn't the same level of concurrency as we have today in Windows. They also used, for virtual memory, segmentation. Now, you might be wondering, did that cause them a problem? And actually, it didn't. So I used Windows 3.1 a fair bit. And I can't say that the fragmentation of physical memory was ever a problem. And part of the reason was you have to think of how people used Windows 3.1 back in the day. This doesn't have true preemptive concurrency. So you're not going to have 20 Netscape navigators open and all watching YouTube at the same time. That's just not possible. That was never possible. And the thought that you could even do that didn't really come to anybody's attention. Like, I remember using the internet in Windows 3.1 and Netscape Navigator. The concept of having two Netscape Navigator windows open was very bizarre, and I think it wasn't until Windows 95 that we ever even tried to do that. In Windows 3.1, we just kind of ran one program at a time, or maybe Netscape and Notepad or something like that. But there wasn't a lot of users actually trying to do concurrent applications, so it wasn't a big deal. Now, what's interesting about Windows 3.1 is that even though it's massively deprecated, it's actually still used today. And the reason why it's still used today is because it's so tiny. In fact, Windows 3.1, I remember installing it on an old 486. It was like 4 floppy disks, not the 5 1/4. I mean the 3 1/2. So each 3 1/2 is 1.44 megs. So you're looking at an operating system install that was about 6 megs. It's tiny. By today's standards, that's more than sufficient to be used as an embedded operating system, which is where you see 3.1 used today in things like airplane entertainment systems and POS devices. I mean, if you ever wonder why the system on an airplane is bad, now you know. It's because it's using a 25-year-old OS. Now, a part of this generation of operating systems from Windows that are built on top of DOS, there's also Windows 95, Windows 98, and the one that everybody wants to forget about because it was so bad, Windows ME. So those are the last of the DOS-based Windows era. And I mean, Windows 95 and Windows 98 and Windows ME, they look more like what you would expect. 95 was meh. 98 worked reasonably well, and ME had a lot of faults. Now, they realized at some point that this version wasn't going to work moving forward because cooperative multitasking wasn't the way forward. They wanted to support 64 bits and so on and so forth. So Microsoft also had a second family of operating systems that was for commercial use, not consumer use. And that was the NT family that actually came to be in 1993. And the NT family was not built on DOS. It was actually its own operating system that had a DOS emulator in it for those individuals who still wanted to run DOS-based programs. And the NT family was supported 32-bit and 64-bit. It was designed for portability. It did virtual addressing with paging. It had preemptive multitasking. It was more of an operating system as we would think of today. And so after Windows ME, Windows 2000, so NT family and the DOS-based Windows 95, they were actually out at the same time. I know my high school had some labs with like Windows NT, and then they had some labs with Windows 95 or 98. The NT labs were always better because they performed so much better than the Windows 95 or Windows 98 labs. And then after Windows ME, Microsoft officially dropped the DOS-based ones, and they started releasing just the NT family and rebranding them as things like 2000, XP, Vista, and so on and so forth. Now, one of the interesting things kind of about the NT family is, and we've mentioned this concept of backwards compatibility before when we talked about OS2 Warp. If you want big companies to use your products and keep up to date and keep buying new versions, you have to make sure that all of the software that they currently runs exactly the same on your new OS. Otherwise, they're not going to pay for the risk of upgrading unless they absolutely are forced to. And if you actually look at the NT family of operating systems, they are backwards compatible with applications from other older versions of Windows via emulation. So it used to be in Windows that you could right-click on something and say run as. I don't remember because I haven't done this in a long time. I don't actually really use Windows machines. But you could click on like this run as, and then you could choose which version of Windows you wanted to run it on. And that was kind of a neat feature, because if you had like an older video game, you could run it as if you could run as Windows 95 or something, and it would make things work reasonably well. True story. The only Windows machine I actually use right now is my little Surface that's sitting beside me with Twitch open, and I'm pretty sure that's the only thing I actually use it for, is to monitor the Twitch chat. All right. So, showed you Windows 1. This is my personal favorite, Windows 3.1, and it had so fun games. Like, it had this skiing game, Minesweeper. Everybody loved this old version of Minesweeper. There were so many fun games for this. This was a pretty fun OS. And then, of course, we go to Windows 10 today. Now, the reason why I like to show this progression is, remember how I showed the progression of macOS, and how even though from the beginning to today, there's a consistent look and feel that doesn't exist with Microsoft Windows. They keep trying to reinvent the UI. And now with Windows 10, an interesting thing is they actually have two separate UIs kind of built in here. And I don't remember what the name of the other one is. So there's the traditional style with the start menu in the corner. I want to say traditional, but it's not that traditional. And then there's actually a second UI for like a tablet style operation. And so you can switch some computers into the tablet one, and I've forgotten the name of the UI for it. There's a name for it. Metro, that's it. So you can use it all in like Metro mode, or you can use it in like the traditional mode. And one of the things that gets really confusing about having two separate UIs is the fact that some settings are only available through Metro and some are only available through the old-fashioned way. And it's always confusing which settings do you need to go through to actually change the thing you want. So, there, ranting about Windows. All right. So, no episode recap today because we are starting something new. So, let us go over to our new slides. Which are the lovely file systems. Now, file systems are actually a really important topic because you need to store data on a disk in some way. And we know that because we want persistent storage. If I go to BitTorrent and I download something, I don't want to have to download it after I reboot my computer. I want the thing I downloaded to stay on my hard drive. And furthermore, I want to be able to find it on my hard drive when I reboot my computer. So what file systems are is we're talking about how data is stored on disk, but it's not just about how the actual bits are stored on the disk. It's also about how do you construct something to help you find the files on the disk, because retrieving the files is just as important as actually being able to store the files. So there's a few terms. Most of you have heard of these terms that we should. You know what a file is. That's a persistent named object. It's a thing. On your desktop, it's the little page icon. Maybe it depends on your OS. And what's interesting about a file is even though we know it's this thing that we're storing on the disk persistently, we always associate the file as just being, okay, the file is just the program, the data. So if I've downloaded a film, it's just the film's data, the individual frames. But actually, that's not true. There's actually a lot of metadata that's associated with the file that helps the file be a part of your file system. So metadata is things like the file type, the timestamps. So what time was this file created? What time was this file last accessed? What time was this file last modified? Access controls, i.e. permissions. Who has permissions to read, to write, to execute this file? All of those little bits of metadata are actually stored with the file as well, and they're just as important as the file data. The other interesting thing about a file is when you're designing a file system, you have to recall that a file size may change over time. So files can shrink in size and they can grow in size. So whatever you're doing has to be able to support that. Now, let's talk about what is a file system then. So, the textbook definition, I've given it to you here. The data structures and algorithms used to store, retrieve, and access files. Okay. But that's actually a pretty high-level description. File systems can actually be divided into 3 different levels. The top level, the level that you interact with, is called the logical file system. And the logical file system is that high-level API, what a user sees to interact with their files. So, for example, if I open Finder here, and I go to something like my desktop, or maybe I go to my code directory, seeing on Reddit there, they're saying you're not a real prof if you don't have at least 3 projects in your GitHub repo. Okay, well, maybe I'm not a real prof then because I don't have a GitHub repo. I hate Git. But here you go. Here's my active project code directory, so I'll let you guys be the judge. All the active coding projects I'm working on right now. Yes, it's a lot. So I'm interacting with my file system right now in Finder. I can go into a folder. So let's go into Spline. That's a favorite. And so by double clicking on that folder, I am traversing my file system looking for something. And I can, let's look at this image, strokes dot. See, oh look, it's a pretty sketchy drawn circle. That's a pretty picture, so I can open the file. But what else can I do with this file in here? I can right click and I can get info. And this is actually spitting out a lot of the metadata that belongs to this file. So here you can see this is a PNG image, because if you're doing anything in computer graphics, you should probably use PNG or SVG. It tells me the size, the actual size in bytes and the size on disk. Yes, I am aware that these two values are different. We will talk about why they are different a little bit later. It tells me when my file was created. It tells me when it was last modified. I haven't actually played in this directory for a few weeks. It tells me information about last opened, the dimensions. It tells me the color space and all kinds of other wonderful information about this particular file. And then, of course, I could go to my terminal. And this is a piece of code that I was working on last night. Yes. Somebody saw on Twitch here, I have a folder called Fake News Sentiment. My grad student and I are working on fake news detection and sentiment analysis. I might be a graphics person, but that doesn't mean I do only graphics research. I actually really like NLP as well. Okay, so I can go into this directory here called Decompose Layers, and I can ls, and that's showing me the files that are in here. And I can use -LA to actually show me information about those files, creation date, size, permissions. All of these operations that I just did are all a part of the logical file system. But I want to show you some more operations. So let's actually open main.cpp. I had started working on this piece of code last night. And what you can see here is I have these commands, imread. Now, I know you're probably not familiar with the program called OpenCV. I'm going to call it an image library, but it does more than images. Anyways, imread is going to open this image file as a grayscale image. This opens a file. imread is opening a file. Opening a file is a part of the logical file system. So the command imread, the command open, the function close and read and write, those are all part of the logical file system. So the thing about the logical file system is that it doesn't actually tell us anything about how the file is stored on the disk. Gotta find my right file here. So the logical file system is just the high-level abstracted functionality that's provided to users. So what's nice about a logical file system is I don't need to know anything about the underlying files. I don't need to know what physical file system they're stored on. I don't even really need to know what drive they're on. The logical file system is this really high-level abstraction provided to the user, so they don't even have to think about things like that. Now, below the logical file system, we'll take a closer look at some of the functions in it in a few minutes. We have the virtual file system, which is actually optional. But the virtual file system is going to take a bunch of physical file systems, which we haven't mentioned yet, and it's going to present them to the logical file system in a consistent way. So I want to show you that in Finder here. So what you'll see here is on my left, I actually have a bunch of things. So I've got text analysis. These are my favorites. Should probably remove CS136 from the list. Remove from sidebar because I don't need to worry about that course for a while. And let's remove CS135 from the list. So you'll see here, I also have some network locations. So I have something called Sangria. And this is not on my computer. So Sangria is actually a network attached storage device. You'll notice that I just connected to it. And I didn't even need to be aware it was a separate device. It's in my basement. And I didn't need to know that. And I can go through this. I'm not going to go through this. Obviously, this is my private storage device, but I can go through this and I can navigate this and manipulate the files in this as if they were sitting on my computer. And it's the virtual file system that has presented my NAS and my actual physical drive in the computer together as the same thing almost. And we'll talk about more how you do that a little bit later. Always helps to open the right thing. Okay. The final level of a file system is the physical file system. This one is required. Virtual file systems aren't necessary, but a physical file system is. Now, when you think of file systems, a lot of you are probably thinking NTFS, or FAT32, or exFAT, or ext3 or ext4. You're probably thinking of those names. Those are not the names of logical or virtual file systems. Those are the names of the physical file systems. And the physical file system is how the data is actually stored on the physical media. So how do we actually write the bits and bytes to the drive such that it stays there and we can retrieve it at a later date? And there's lots of different physical file systems. So NTFS, for those of you who may not be aware, that is the Windows journaled file system. ext3, ext4, those are journaled file systems that are typically used with GNU Linux, but they don't have to be. There is HFS and HFS Plus and APFS, which are all file systems used with Apple products. If you're running anything newer than High Sierra on your Apple laptop, then you are actually using APFS. There's many different file systems out there. FAT32 and FAT16 are the old non-journaled Windows file systems, and we'll actually talk more about them later because they're actually pretty interesting. And exFAT's an extension to FAT32. There's others out there still yet. There's log structured file systems like S3, which is used by Amazon, which has its own quirks. And then there's a file system called RiserFS, which many years ago I used to use. I don't use it anymore because the individual who created RiserFS is actually in prison for murder. And once he went to jail for that file system kind of fell off. It was one of the first really great journaled, reliable file systems for the Linux kernel. And if you got it to work, it was super fast and super reliable. And then the guy killed his wife, and people stopped using it. And I think a lot of the tech that was in Riser has actually filtered its way into ext3 and ext4. I think, but I'm not 100%. It's still around, by the way, RiserFS. All right. There's lots of file systems out there. That's what I want to point out to you. And for the individual on Twitch, that escalated quickly. I mean, what, did you think people who write code are all boring? All right. So let's take a closer look at the logical file system. This is stuff you know. Maybe you haven't done it before. Maybe you have. Open. Opens a file. What does it actually do? So open is actually a little bit more complicated than what you might think. What happens when you open a file? So when you open a file, and we'll actually see this in great detail later, probably on Thursday, you first have to find the file on the disk. So you are giving open a path, which is telling it, where can I find this file? So open is going to find the file. And what's interesting is each file has a file identifier, a handle or a descriptor, which is usually related to a file's unique I number. Every file in your file system actually has a unique number. Because inside of your computer, do you honestly think we want to use strings to refer to files, or do you think we want to use numbers? One's a lot faster than the other. So internally, files are referenced by their numbers. So open is going to have to find the file that corresponds, the file number that corresponds to the path that you give it. And then it's going to create a file identifier, which is also known as a handle or a descriptor. And I want to say that a file handle or file descriptor is the most appropriate term here. Now, Open is going to return that to you. And that is how you're going to refer to that file from that point forward. You will never use the name of the file to refer to it after that, because the name is too slow, because it's a string and it requires a lookup. When you open a file, after you've found that file, created the file identifier, other things happen. In your process structure, there's an open file table. Well, it's not actually an open file table. It's a file descriptor table or a file handle table. The file descriptor table, the file handle table, keeps track of every file that the process has open and what is your current position in that file. So it's not an open file table. It's a file handle or file descriptor table. So when you open a file, you're going to add that file handle to the file handle table in the process structure. And then the kernel has an open file table. And the open file table keeps track of how many processes or threads have each file open. So if a file is open, we will keep a count as to how many people have it open. Now, you may have encountered this in a bad way in Windows. So let's suppose you plug in external storage and you do the right thing when you are done and you safely eject. And by the way, it is actually really important that you safely eject or safely unmount file systems that you attach. We'll talk more about that later, but it is really important you do that. But let's suppose you do that in Windows. Many of you may have encountered, safely unmount, and Windows pops up a little error box that says, file is still in use. But you look at your computer and you're like, I closed every program. Everything is done. Why can't I unmount the file? So what you do is you pull it out, which is bad. But what other choice do you have? So the reason why that message comes up is because in the open file table in the kernel, it's still indicating that there's somebody that has the file open. So that's an interesting quirk. All right. Usually, by the way, what ends up happening is if you don't call close on a file, you may not properly close the file. So let's just do an overview of open. Open is going to use the path you provided to get the unique identifying number of the file. It creates a file handle or file descriptor, and then it is going to add that file handle or descriptor to the file descriptor table that is located in the process, and then set the initial start point for a file to be byte 0. We'll talk more about that in a minute. And then in the open file table of your kernel, we're also going to indicate that this file is now open and that either one more process has it open or this is the first process that has it open. Okay. Open does a lot. Now what close does is close is going to invalidate the file descriptor that is in the file descriptor table of the process, so we can actually remove it from the file descriptor table of the process, or we could just invalidate it. And then we also have to remove or decrement the counter for the kernel's open file table because one less process now has it open. So we're going to decrement that as well. So if you don't close, some of these tables may not be updated correctly. And that can be pretty bad. It can have some pretty bad ramifications later on. Actually, not closing your file has some other consequences as well, which we'll talk about later. All right. Now you have the operations read, write, and seek. Read, of course, is going to read data from the file. Write is how we write data to the file. And seek is going to let us read and write the file from a specific position. Because what's really interesting about read and write is they are sequential operations. What that means is that if you do a read, you don't actually tell read or write where to read or write from. You simply pass read or write, the file handle, and how much bytes you want to read or write. You don't tell it where to start reading the file from, which means that each read happens from the place where the previous read or write left off. Now, how do you know where the previous read or write left off? Well, that information, the current file position, is stored in the file descriptor table in the process. There's good reason we have it. Then we have a bunch of other commands called get and set, and fstat and chmod and ls and la, and these are all logical file operations for reading and writing and modifying the metadata associated with the file. I'll come back to seek in a minute, by the way. So many of you, or some of you at least, have often wondered why in CS350 we do not permit individuals to use the timestamp from the terminal to indicate that you have not modified your assignment submissions since the deadline. Some people accidentally submit the wrong files, things like that happen. Let me show you why we don't permit timestamps. So let's leave this file here. Let's suppose that you were trying to pick a course. Let's suppose that you were taking an SPCOM course. Well, maybe not SPCOM. I don't want to pick on that. Let's suppose, we'll do another example. Let's suppose that you're a graduate student or you're doing some undergrad research for a professor. And you were supposed to have your final research result to your professor on March 10th, the day before the university went under lockdown. Okay. But you didn't do it. And you get an email from your professor, your supervisor, finally, and he says, "You didn't send me the result. You didn't do the results for the project. I never received your final report. I need to submit your final grade, so please submit it to me now. Why didn't you send it? Did you not do it?" Now, you don't want to seem like a bad student who hasn't even started the project yet. Oops. So you've got to find a quick and dirty way to trick your professor into thinking that you did the project and you did it on time and you submitted it to them. He just lost it in his email. So you go and you do your project. Go, there's the project. And you'll see here, I project.txt, and it is 0 bytes in size, but let's pretend it actually has something in it. And you'll see that its creation date was November 24th at 10:10 a.m. Wonderful. But that's the problem. If I submit this file to my supervisor, they're going to see that the file was created on November 24th at 10:10 a.m., and they will know instantly that I didn't do my work and that I only just did it. I don't want them to know that. I want them to think they lost the email or it got caught by a spam filter somewhere. I want to absolve myself of all fault. So watch this. Using the same command that we just did to create the file, let's change the date. So it was supposed to be submitted on March 10th, and I don't want to make it seem like I did it at the last minute. So let's suppose we created it on, well, if I submit it on March 10th, maybe I wanted it created on March 3rd. March is the third month. And I want it made on March 3rd. Now, what time should this file be created? If it's really early in the morning or really, really late at night, I look like a bad worker that either stayed up too late or was awake all night working really hard to get this done. So I want to make the timestamp look like I'm a very reasonable individual. So what if I made it created at, say, 9 in the morning? But I don't want to use a multiple of 5 because that looks suspicious. So let's say at 9:43. Great. So let's do this. 0943. Okay? Now, look at that. Looks like I set the time wrong. Let's try setting that time again. Maybe not 9:43. Let's do 10:43. Oh, I don't know why it's doing that. Anyways, sometimes Apple's shell doesn't work quite how you expect it. Anyways, even though it's not showing me the time does exist. And so now my project file says March 3rd. So then I put my answers in it and I send it off to my supervisor and I say, hey, I did do it on time. I'm so sorry. It must have gotten lost in your email, but here's another copy just in case you can't find it. And of course, your professor isn't going to go looking through their thousands of emails that they got between March 10th and today. They're just going to take the one that you just submitted them and grade that. So, now you know why we don't accept time stamps as proof that you haven't done any modifications to your assignment, because it is trivial to change them. Now, there's lots of other different metadata commands we could use. We could do a command to change the permission. So right now, if you look, you'll see this just goes users, group, others. So I have permission to read and write the file, and other people of other groups have permissions to read the file, and other users have permissions to read the file, but nobody else has permissions to write this file. I can actually change that with a command called chmod. Now, there's different ways that you can do chmod. There's numerical codes like 777, which gives all permissions. Like that. I don't remember all the numerical codes. There's some way of doing them. I don't remember them. I prefer to do the much more user-friendly way of saying UGO minus X. So that will remove execute permissions from users, groups, and others. So that makes a little bit more sense to me. So now you can go back and see we've removed execution privileges for everybody, because you shouldn't be able to execute a text file. That makes no sense. And there are tons more other metadata functions that you can use to modify your file. So that's kind of cool, right? Now I want to talk about seek. So we mentioned that read and write do sequential reads and writes of the data. But that means that, let's suppose you want to open a file and you want to read a specific byte. You don't want to start reading at 0 and then have to read every byte up till byte 10,500 to finally get byte 10,500. You just want to read byte 10,500. Seek can help you with that. Comment on Twitch is saying each digit in chmod is binary for one set of permissions. I believe you. I learned this once many, many years ago in CS241. I have forgotten it. And I just prefer the text-based one. So it's great if you know it. Or you can use the letter-based one, which is readable by a human. All right, so seek. So read and write are going to do their read or write starting at the position listed in the file descriptor table of the process. So if the file descriptor says we are at position 0, then the read is going to start at position 0. But if I want to read byte 10,500, I don't want to have to actually read the 10,499 bytes that preceded that byte just to get to the byte I want. I just want to read 10,500. That's what seek lets you do. Seek lets you move the current position in the file to whatever byte you want. Now, a lot of people think that seek is going to actually go to the file and check to make sure that this byte is a valid byte, but it doesn't. So what seek actually does is it opens that entry in the file descriptor table of the process, and it changes the current file position to whatever byte you put. And that means that seek, or lseek as it's more commonly known by, because it doesn't actually check against the real file size, you can seek beyond the end of the file. And no error happens. Nothing bad happens. And the reason nothing bad happens is because all seek does is modify the file descriptor entry in the file descriptor table. That's it. That's all it does. It modifies it. It doesn't touch the file itself. It's on the next read or write or file manipulation operation where any error would actually occur. So if you wanted to read byte 10,500 of our file project.txt, which has 0 bytes, and you seek to that position, no error happens. But then if I try to read from 10,500, that's when the error actually happens. So it's kind of a fun thing. So we have a couple examples here of just to very quickly show you what's going on. And I actually prefer to draw these out. So I'm going to put these notes over here. And I'm going to bring up OneNote, and hopefully it doesn't crash on me. Which you all know is totally going to crash on me, because that's what OneNote does. It crashes on you. First, it crashes by not letting you resize it. Okay. Probably should have started my tablet up earlier. My little writing tablet always has a hard time connecting because my son, who's 2, loves to come over to my desk and push every button he can get his little hands on. And he's quite tall, so he can reach all the way to the back of my desk, and he loves pushing the buttons on this thing, so it's always in a funny state. And my microphone, if you're ever wondering why my microphone is quiet, is because he comes over and he plays with the dial on it too. So, all right. So, new page. So we have this little piece of code here, and it says we're going to read from the file 512 bytes at a time. So essentially what we're going to do is, if our file looks like this, we're not going to do 512 bytes because I'm too lazy to write that many letters. Also, the English language does not have that many letters. And I don't know any other alphabets. So let's say we're going to do it instead of 512 bytes, let's do 3 bytes. Then what this code does is when you open the file, the current file position will be right here. So we'll call it CFP, current file position, so at position 0. And then if we do reads of 3 bytes, then we'll read this first, and then my current file position will be here. And then I will read this one second. You can see how the current file position is advancing as we read, and that happens silently for you. There's my 3rd read, and after my 4th read, you can see that my current file position is now here at the end of the file. So that's what we mean by sequential reads and writes. We're not telling it where to read and write from. The file descriptor in the file descriptor table of the process indicates the current file position. Now here's a fun one that uses seek. So we'll do this one in a different color. Let's do this one in black and blue. So same file. Now what you see happening here is we seek to some position before we do the read. So current file position would normally start after you open the file here, right? But the first thing that we do is we actually, with the else seek operation, move the current file position here. And then we read this. So that gets read first. And then I move the file position over here. And this gets read second. And I know these arrows are getting very, very complicated. Then I'm going to move the file pointer here. And I read DEF, so that's 3rd. And then I move the file pointer finally all the way back here, and I read ABC last. So the second one, by using the seek operator, lets us read the file backwards 3 bytes or 512 bytes at a time. So that's kind of fun. All right. These operations are ones that you're fairly familiar with, but if you want to play around with them, I highly encourage you to do so. Don't do it in OS 161. Actually, do it in C or C++. Play around with the seek operation. Some fun things that you could try to play with seek is see what happens if you seek beyond the end of a file and read or write. See what kinds of errors that you actually get come up. That's kind of a fun thing to do. All right. So that's all we're going to really talk about with the logical file system for today. So let's move on, and I want to talk about directories and file names, which this is kind of part of the logical file system as well. But it's also just describing how are we going to map a name to the file number. So first off, when we think of a directory, I mean, when you're thinking of a directory, you're thinking of, you open up Finder, and on mine, they're little blue icons. So I go to my code directory, and oh, look, there's these little teeny tiny blue icons, which you probably can't see. Let's make them bigger here. Look at them, aren't they beautiful? They're blue folders. That's what we picture when we think of a directory. I know your folders probably don't have these lovely green check marks. That's because all my data gets automatically backed up to my NAS, okay? And the green check mark means it's up to date on my backup system. So we think of directories as these containment units, where it's like if I open, let's say, SVG, I'm expecting there to be SVGs in here. Apparently there aren't. Or if I open, stereo tests, I know that inside my stereo tests folder, that I have all of my stereo test images. So I am looking at, let's do, I don't know, stereo test 3. Oh, it's the ugly cups. So inside here, I know that this is a stereo 3D image that I use for testing, and it's hideous and ugly, but it works, right? Test images and graphics are always hideous, for the record. So we use directories from a human perspective as a means of organizing our data. But in terms of what your computer uses the directories for, it's actually a bit different. So directories to us are for organization, and they do organize things. But what is actually in a directory, what a directory actually is a mapping between file names and their unique identifying numbers. So inside of a file, a directory, what you actually have is something like foo.txt is file 87. And bar.txt is file 999. And directory blah is file 876. So a directory maps the string name of the file to its unique identifying number. Now, what's really cool is that if we go over to my terminal again, we can actually open a directory as a file. So I've got a bunch of directories here. I'm going to open Edgewalker. Helps if I can spell. Now, it's not going to show me what number my file maps to inside of here, but as you can see inside this directory file, a directory is a file, by the way, has the list of all of the things that are actually contained in that directory. And then it's hidden from us, but the file number is also accessible here. By the way, you cannot edit those files. It's not allowed. All right. So a directory contains a mapping between the file name and the unique identifying number. We actually have a formal name for that. It's called a hard link. So what's interesting is that our paths, if you look at your file system here, and if I look at, so my file system here, I can go to computer, which is root. So here I have, this is my Macintosh hard drive. I can double click on this. That's the root of a tree. And so that's my root. And then inside of that, I have four children. I have applications, library, system, and users. And then I can click on users. And inside that, you can see I have guest. I have myself, which is Lenortha. We have Professor Neckbeard. We have shared, and we have teaching. And if you're wondering, why do I have a user called Professor Neckbeard? My husband was using my laptop. And that's the username you wanted. Anyways. So you've got the root, and then you've got those 4 children, and then the user has these 5 children, and then we can go into each of these, and they've got children. Your file system, this path, it actually creates a tree. We call it the namespace hierarchy. So we can actually, that's the wrong one, we can actually draw it out. So if you look at it, this is this hierarchical namespace. It forms a tree. So there's the root at the top, and then there's the children as the directories you find in there, and their children, and their children, and their children. So you actually get this neat tree. And then what a path is the path that you take through this tree to get the file ID number. That's all it is. So when you are opening a file and you pass it a path, open starts at the root. And then it looks at the next component of your path and it says, oh, foo. And so it opens foo. And then it sees that the next part of the path is misc, so it opens misc. And then it sees that the next part of the file is temp, so it opens, or the path is temp, so it opens. It finds that foo misc temp is file number 12. So that path is the path you take through this tree to map a string file name to the file ID number. It's pretty cool, right? It gets more interesting. So a few things to note about this namespace tree. So you'll note that files, as in actual data files, can only be leaves. Internal nodes can only be directories because a directory contains things. It's what maps the string, the path, the file name to the I number. So a directory can be an internal node. It can also be a leaf because a directory doesn't have to contain anything. But files themselves, actual data files, can only be leaves. They are not permitted to be internal nodes of our tree. Another thing to note is that every file, every directory, which is also a file, they have to have a unique I number. We call these I numbers. Okay. No 2 files can have the same I number. But now things get really interesting. Sometimes when you install something like GCC, it gets installed into a really bizarre place. Or it has a really long name. Like if you look on my computer, just a minute. So if I look for GCC, you'll see I've got GCC and GCC-10. And when I'm using GCC, when I compile, I don't want to have to type the version code with it. Same with Python. So like if I do Python, because I've been writing Python code lately, I'm ashamed to say it. Sorry. I know many people like Python. I don't like white space sensitive languages. So if I want to use Python, I'm not going to type Python 3.8. I don't want to do that. And I don't want to have to type the path that it's in. What I want is an easier way to access GCC or Python without having to type its long-winded path, without having to type all the 3.8. I want to give it a simple name and I want to toss it in my bin directory because I don't want to modify my path on my system. We can do that. We can actually do something really, really cool here. We can have multiple hard links to the same file. Now, what does that mean? Now, remember, the hard link is the mapping that is contained in the directory between a string and the I number. So, I can create multiple hard links to the same file. For example, I can create docs. So I have docs my A. That is the one path to file 147. I can create another hard link that says foo my a 147. All I have to do is in directory foo, I add a hard link that says my a 147, because the directory isn't actually like a box that you put things in. It's not a data structure that you're putting shit in. The files don't actually live in the directory. The only thing that the directory contains is the mapping between the string and the number. The file itself isn't in that box. So into directory foo, I say my A147. And now I can access file 147 by docs.a.txt or foo my A. Or if I was doing something on like my computer here, what I would have is because I actually have 2 versions of GCC installed. Don't believe me? Here we go. See there? I've got 2 versions of GCC. I've got one in my local bin, but maybe I want this GCC to live in bin. I can add a hard link. I can add a hard link for GCC 10. I can add it to user bin GCC or user bin. And now it's in bin, sort of. So this can actually be really useful when you install extra tools to actually create multiple hard links. Now, true story, I don't usually create hard links to things. Creating hard links to things, I want to say, is not something most people do these days. And as far as I know, now again, I am not a big Windows user, so I don't believe you can actually do this in NTFS or on a Windows system, but you can definitely do it on any Unix-based OS. There are some rules, however. You are not allowed to create a hard link to a directory. It's not that all possible hard links to directories are bad. It's just that you don't want to create any cycles. Let me show you. So let's suppose that we have directory foo. And inside directory foo, I have a file bar.txt, which is file 87. And I also have directory ccc, that is file number 71. And foo, we'll say, is 40. Okay. And then inside directory ccc, which is number 71, I have a link to foo, which is 40. Okay. So the question I have for you is, how many paths to bar.txt exist? Because this is what our tree looks like. So here's foo. So we'll write 40 here. And here is ccc. And here is bar.txt, so there's 87. Now, inside of file 71, I have a link back to 40. So how many valid paths to file 87 are there? Well, let's list some. There's foo bar. There's foo ccc bar, or foo ccc foo bar. There's foo ccc foo ccc foo bar. Do you see that problem? We now have an infinite number of paths that are valid to file 87. And if you go on a Mac and click all my files, that means that your system takes forever trying to find every file. Cycles in the namespace tree can be a bad thing. So to prevent cycles, we don't permit hard links to directories. Now, or multiple hard links to directories. So here's the thing. You could be smart about it, because it's not always going to be bad. I might simply create, instead of creating a loop here, maybe I did something like, okay, well, I've got my file here, and I've got a directory here, and I've got a directory here. And maybe I've got another directory over here. and maybe I'm going to create a second hard link here. This isn't bad. This isn't bad. But if I want to permit things like this to happen, I need to, when I create the hard link, check if there's a cycle. And I'm sure as many of you have taken CS341, that checking for cycles isn't necessarily a cheap thing to do. So one of the ways to prevent us from having to check for cycles is to simply not permit the creation of multiple hard links to directories. Now, that doesn't mean that there's no OS out there that doesn't permit it. I'm just saying, generally, we're not going to. All right. Now, you generally create a new hard link. I think we gave the command here is link. There's a few different ways to create multiple hard links. What if I want to remove a hard link? Like, let's say I don't want foo.my.a to exist anymore. I just want docs.a.txt to exist. Well, there is a command called unlink. And unlink is going to remove the hard link from the directory. So we would actually go into the foo directory and we would remove the mapping from my.a to 147. Now that, you might be thinking, deletes the file, but it doesn't necessarily delete the file. If there are no more hard links to the file, then the file would no longer be accessible and we should delete it. If, however, there are still hard links to the file is not altered. Unlinking doesn't necessarily delete the file. Now, another true story is even if, let's suppose we try to unlink, I guess in the example on the next slide, it said docs.b.doc. If I unlock docs.b.doc, because there would be no more links, then I should delete this file. Now, what does it mean to delete the file? You might be thinking, oh, well, we've got to remove all the file data and clear it out. I really hate to tell you this, but that is absolutely not what deleting a file usually does. Usually when you delete a file, you're unlinking it, so it's no longer in the namespace tree, which means it can no longer be retrieved. And we are going to mark the blocks of data used by that file as being free, but we don't actually clear it out. So that file, we're not going to actually overwrite the data or clear the data unless you explicitly tell it to. So there's this concept, and we'll talk more about it another day, called secure delete. If you just delete a file, the data's technically still there, you just can't access it. If you secure delete the file, you can't access the file and the data gets deleted. It's like quick format versus low level format. Quick format just gets rid of this namespace tree. Low level format gets rid of the namespace tree and clears the data off. So never, ever, ever actually get rid of your disk unless you've done a low-level format. The government has gotten themselves into trouble on numerous occasions because they were getting rid of old hard drives and they just did a quick format. And the quick format doesn't actually get rid of the data. It just gets rid of this tree. And you can still retrieve the data from the disk. It's because it's still there. So yeah. Private data has been leaked because people did a quick format instead of a proper format. So always make sure you do proper formats. All right. One last thing before we go. I want to talk about virtual file systems. So that's our discussion on logical file systems. Now I want to do a very brief discussion of virtual file systems because it's really quick. There's not much to it. So the idea of virtual file systems is we're going to take multiple physical file systems and present them as one common thing to the logical file system. I don't want the logical file system to have to think about, oh, well, I can't use this version of open on this file system because it's different. No, we don't want the logical file system to even know. So how do you do this? Well, there's two different approaches that you can do. There's the Windows version, which actually makes file names have two parts. So let's look. So many of you I know have used Windows before. I don't know many people who haven't used Windows, to be honest. But if you wanted to access a file on your computer, you do C:/Win32. Don't write in this directory. All right, there we go. So what I have here is a path to a file. Now here's another path to a file. there's a path to my movie. And here is another path. Oops, I can't spell. Here's an old game I really like. Zaxxon.exe. Okay. These 3 different files actually live on 3 completely different disks. How do I know that? Because the file names in Windows have 2 parts. The first part is the drive or file system level. It tells me on which device or which file system should I be looking to find this path. So essentially, you've got some root, and then you've got C, D, A. And then there's all your stuff on C, all your stuff on D, and all your stuff on A. So 2-part file system. You've got your file system ID, and then you've got, of course, your path. Now, Windows has used letters to do file system IDs, and now I think you can actually do longer names, although, again, I don't use Windows too often. When I was younger and I used Windows, you could only use the letters of the alphabet. You couldn't do anything more than that. So that gave you 26 options for file system names. I don't know many. Actually, that's not true. I do know some people who actually max that out. It happens. But some of you, here's a quirk. How many of you have ever wondered, why does the file system C? Why does it drive C? Whatever happened to drive A or drive B? Why is it always drive C? When you install Windows, it's always drive C. Why? There's a reason. The very first personal computers that were released, and I actually had one, didn't by default come with a hard drive. It just came with one floppy drive or 2 floppy drives, depending on what you wanted. And because floppy disks, like most people didn't have hard drives and they didn't come out till later, floppy drives were given the letters A and B. And then later, so probably around 85 to 86, I want to say people started purchasing hard drives. So like my old IBM didn't have a hard drive. And yes, you can have a computer that doesn't have a hard drive. It just means that you either have to have DOS in one drive and your game in the other, or all of your games or programs have to be self-bootable. And most of them were self-bootable. So A and B were for floppy drives because they came first, and then people started getting hard drives in the mid 80s, and I mean they were huge. Like you're looking at like a hard drive this big, it weighs about 20 or 30 pounds, and it stores 5 megs. I actually had one. It was really cool. So since A and B were floppies, and everybody had floppy drives because you had to have floppy drives, the next drive letter was C. And even though we don't use floppy drives anymore, it's just kind of, I want to say habit. So the hard drive is C. And then when we got CD drives, that became D. Now my 486 actually had 2 hard drives. So my hard drives were C and D, and then my CD drive was E. And then it was really common back in the mid-90s for the network drive to be N or Z. So there you go. That's how Windows handles the virtual file system. So we use a 2-part path, where the first part of the path identifies the file system, and the second part is the path on that file system. Now, how this is done on a Unix-based file system is different. So on Unix, we're going to attach, but it's not a real attachment. We are going to create a single hierarchical namespace combining the namespaces of the 2 separate file systems. And this is what mount actually does. Now, it doesn't make it one file system. We're just combining temporarily the 2 trees. So here's an example. So mount, you can actually mount a file system, if you've ever done this, wherever you want. So if I want to take file system X, so this is my host file system, the root, and I want to mount file system X so that I can easily access it. So what I do is I'm going to say, okay, mount file system X, and then I give it the path from my host file system of where I want it to be mounted. And what it's going to do is it's going to take the namespace tree for file system X and it's going to attach it, as you can see here, underneath XA. Now you can't attach it to a file because that doesn't make sense. Files shouldn't contain hard links, and it's not containing a hard link, but you can attach it into a directory here. So XA is where I can find file system X inside that. And then if you unmount, it detaches this tree from there. Now, one of the interesting things about this is you might be wondering, well, what if on file system X, file XQ is file 87, and on our host file system, what if ZC is file 87? Wouldn't you then have two 87s in your tree? And I mean, at first glance, you do. But in reality, you don't, because the system is going to keep track of the fact that if you go down this path XA, that is a different file system. So it will not confuse this file 87 with this file 87 over here. So internally, we keep track that they're separate. All right. So that is the end of logical and virtual file systems. Fun, right? We got through that really quickly. In our next episode, we are going to start talking about physical file systems, which is super exciting because everybody likes physical file systems. We will look at a Unix-based file system, which is pretty interesting. And if we have time, we'll also look at FAT32, which is a really interesting file system as well. So we will see you on Thursday with hopefully also more details of our wonderful guest speaker as well.
Stop. Hang on. Wait. One more thing. Hi. I'm FEC. Is there time for questions? Good, because I have one. Why? Why make all these advancements? What's the point? Right? Oh, you're so quiet now. Look, I'm a machine. I'm proud of it. That's my fan. Longer battery life. Plug it in. Where are you going? Just plug it in. Fast. I'm fast. I'm still fast. Check it out. Still got it. PC. Still got it. I've always been there. I always will be. Fast. Okay. My battery's drained. I gotta go plug in. Good luck.